Hello, this is Mrs. Huntley. This is Module 5, Lesson 1, the concept of a function. You should have your new module, and you're open to the first lesson. Your essential question, how do we use functions? Functions are a concept that we use to make predictions. We use them a lot in science. Math, of course, is the language of science. So when we're doing things like in physics to talk about the science of movement, there's always a mathematical equation, kind of a cause and effect equation that we can put together with whatever's moving and whatever's happening so that we can use our experiences, our experiments, to then make predictions about how things would be in the world, maybe in a different situation. Now, we could also use functions to classify things that are non-number related. For example, there might be a function or a relationship somehow between gender and height, or age and height. Some of those might be functions, might not be functions, so we have to talk about what a function is before we do that. But I just wanted you to know that sometimes functions classify something that's non-number related. It's just a way of classifying data and using that data then to make predictions. So example 1, suppose an object is, suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. That is, the motion of the object is linear with a constant rate of change. Now these words should be familiar to you. Constant rate of change, that's what we dealt with the entire last module. And of course you remember, I hope, that rate of change is also what we call slope. So remember all the equations that we solved in slope-intercept form. This module will be putting those concepts that we learned in the last module to use in kind of some real-world type situations. Okay, so our object travels 256 feet in 4 seconds. Now x is our time. That's our number of seconds. Y is our distance. That's how far it's traveling. So our seconds are already populated in the table. We've got 1 to 4 because we've just been observing this object for 4 seconds. So in 4 seconds, it goes 256 feet. This is kind of like some of the problems that we had in the last module. If I wanted to find out how far it goes in 1 second, what am I going to do? I'm going to take the distance it goes in 4 seconds, 256, and divide it by 4 seconds because that distance should be the same over every single second that it's traveling. So 256 divided by 4 is going to be 64. So my moving object travels 64 feet in 1 second. So in 2 seconds, I'm going to take 64 and multiply by 2. It's going to be 128 feet. And in 3 seconds, it would be 192. Again, I'm taking the distance that it travels at 64 and multiplying it by the number of seconds. So if I want to write a linear equation in 2 variables to represent this situation, how would I do it? Well, I already said my slope and my rate of change are going to be the same thing. And didn't I identify my slope as 256 divided by 4, or 64 over 1? Again, that's 64 feet in 1 second. And that would be my rate of change, or my slope. So if I want to put that in equation, it's going to be y equals 64x, where x is any time I want to plug in there, and y is the distance that it travels. And of course, that's 64, or 64 over 1. That's my m, my slope. Or here, we're going to call it rate of change. Okay? This means that the average speed that that object is traveling is 64 feet per second. And that's kind of what I alluded to over here when I was talking about it. Okay? And none of this is new so far, right? You're like, okay, we're in a new module, but we're kind of talking about the same stuff we talked about in the last module. It's going to get a little different, don't worry. What predictions can we, does this equation allow us to make? We can use this equation to predict the distance traveled in any time interval. So I can choose a different time than 1 through 4. I can choose a fraction of a second. I can say in 1.5 seconds, how far does it go? I plug in 1.5 here and I'll get my distance. So if I graph this, it's going to be a line going up and to the right. Pretty steeply, 64 over 1, so I'd be going up 64 and over to the right 1. I'm guessing that my graph wouldn't be counting by ones, though, because that would be very, very tedious to graph that way. Okay, so again, last module, we focused on situations where the rate of change, the slope, was always constant. We can't always assume that. So we're going to look at a situation where it's not a constant rate of change. Let's go ahead and turn the page. Okay, I know you don't have this little chart over here. I copied it from the front page so that I didn't have to keep flipping back and forth while I'm talking about it. So the object, a stone, is dropped from a height of 256 feet, and it takes exactly 4 seconds for the stone to hit the ground. So let's take a look at a YouTube video of this experiment actually happening, and it's called the physics ball drop. And this was done at, I want to say, a university or a college, where they actually took a ball. It was actually a ball. And they dropped it from the roof of a building. And they recorded it so that they could use that recording to make predictions about how things drop. So let's take a look. I wish I had the ability to slow it down into super slow-mo so you could actually see it at different seconds where it's at and measure it. So I'm going to get rid of that, and we're going to come back to this. Somebody did slow it down into super slow-mo, and they were able to say, where is that ball at 1 second, 2 seconds, 3 seconds, and 4 seconds? And of course, at 4 seconds, it hits the ground. Here's the ground down here. So when they slowed it down into super slow-mo, they found out that at 1 second, that ball had dropped 16 feet. And at 2 seconds, the ball had dropped 64 feet. And at 3 seconds, we were at 144 feet. And at 4 seconds, we hit the ground. Now that is not exactly linear if you look at it. It would be more exponential, and we're kind of curving as we come down. So the interval between times here, this interval and this interval, for the distance that it traveled in the same amount of time, is growing. It's not linear anymore. So we can't really use our linear equation to make predictions about this because we'd be pretty far off. We said in 1 second it was going to travel 64 feet, and it actually took 2 seconds for it to travel 64 feet. And then we said at 3 seconds it would be at 192, and at 3 seconds it was actually only at 144. So our thinking that it was going to travel at the same speed was very far off. So if we were using our equation to make predictions about this situation, we would have been inaccurate. So let's take a look at the questions that we were supposed to answer. How far does the stone drop in the first 3 seconds? Okay, according to the data, the stone dropped 144 feet in the first 3 seconds. And it appears that the stone is picking up speed as it's falling. Let me move that. Choose a prediction that was made about the distance traveled before we learned more about the situation. Was it accurate? Well, if I were talking about the predictions that we used when we were assuming that it was linear, no, because if we assume that it's a constant rate of change or a linear change, our predictions were not accurate. According to the data, how many feet did the stone drop in 3 seconds? The stone dropped 144 feet in 3 seconds. We already talked about that, didn't we? So we're going to just add the answer here. Whoops. 144 feet in 3 seconds. And after 1 second, the stone had only dropped 16 feet. So our estimate at 64 was very inaccurate. After 3.5 seconds, how far did the stone drop? Well, if we look at our table on the other page, we don't know. Again, this is not linear, so we can't just like divide in half the distance that it had dropped between 3 and 4 because it's not going to be dropping at a constant rate. So it's going to be greater than 144 feet and less than 256 feet. Okay, so we can't actually get more accurate than that before we figure out what equation can best represent this data. Let's go ahead and turn the page. Okay. On this page, they're giving us a table. Again, they did super slow-mo the video, and they did record how far the ball had dropped in a half a second, in 1 second, in a second and a half, 2 seconds, etc. And they recorded the distances here. So I'm giving you this data. And they're saying, name 2 predictions that you can make from this table. And I don't like the way they use the word predictions because they're really talking about reiterating the information that's on the table. So if we're using this table to make predictions, I can say every time we drop a ball from a rooftop that's 256 feet, in 3 seconds it's going to be at 144 feet down. It's going to take 4 seconds to hit the ground. Those are some predictions that I can make from this table. Name a prediction that would require more information. Well, if I wanted to know at 3.25 seconds how far the ball is going to drop, I can't precisely say unless I super slow-mo my video or again and I observe it, or unless I figure out what my number relationships are here between these different intervals. So that's what we're going to try to do here. What is the average speed for the object between 0 and 3 seconds? How does this compare to the average speed calculated over the same time interval in example 1? So in 3 seconds, the ball drops 144 feet. So to find that average, I'm going to take 144 and divide it by 3. Okay, so 144 divided by 3 would be 48. How does that compare to the average speed that we said from example 1? Well, we said in 1 second it was going to be at 64 feet. So again, we were off. What does it say? Take a closer look at the data for the falling stone by answering the questions below. How many feet did the stone drop between 0 and 1 seconds? So 0 and 1 is going to be 16 right there. It was pretty easy to answer. How many feet did the stone drop between 1 and 2 seconds? So let's take a look here. At 2 seconds, we were at 64 feet. At 1 second, we were at 16 feet. So I'm going to have to do a little bit of math here. I have to take 64 and subtract 16 because I only want where it was at 1 second, where it was at 2 seconds. I don't want from 0 to 1 second. So 64 minus 16, we're talking 48 feet. So it dropped 48 feet between 1 and 2 seconds. Let's keep going. How many feet did the stone... Okay. Well, I guess I didn't erase it from the last time I recorded this video. How many feet did the stone drop between 2 and 3 seconds? So we're going to have 144 feet minus 64, and that would equal 80 feet. How many feet did the stone drop between 3 and 4 seconds? So again, I'm going to go from 3, which is 196, subtract, 256, subtract 196, and I get 112 feet. Compare the distances the stone dropped from one time interval to the next. What do you notice? And I notice that compare the distances the stone dropped from one time interval to the next. What do you notice? Over each time interval, the distance that it traveled was 32 feet. If it was at 16 feet after 1 second, so 16 feet after 1 second, if I add 32 to that, I get 48, and that's where it was after 2 seconds. If I add 32 to that, 48 plus 32, I get 80, and that's where it was after 3 seconds. If I add 32 to 80, I get 112, and that's where it was after 4 seconds, between 3 and 4 seconds. So each time interval, it's going up by a factor of 32. The difference was 32 feet. Okay? So what I would like you to do is figure out the average speed of the stone for each half-second interval. For example, or for the average speed over the interval. So we're subtracting the 2 time intervals, and then we're dividing by the time. So let's take a look at how to do this, and I will show you. Okay? So between interval 0 and 0.5, looking at the table, it traveled 4 seconds, or 4 feet, I'm sorry, over 0.5 seconds. If I use my calculator, 4 divided by 0.5 is going to be 8 feet. Okay? So that average would be 8 feet. The interval between, part B, the interval between 0.5 and 1. So at 0.5, or excuse me, at 1 second, we're at 16. At 0.5, we are at 4, so 16 minus 4, and divide that by the time interval, which again is 0.5. So 16 minus 4 is 12, and 12 divided by 0.5 is going to be 24 feet. Where am I getting the 16 and the 4? If I look back at this table, at 1 second, I'm at 16. At a half second, I was at 4. So I'm going to subtract those to find just that time interval and then divide it by that half second. So we're going to go ahead and calculate these for C through G. I will do the next one with you, but as soon as you feel comfortable, what I would like you to do is go ahead and pause the video and start working on these on your own. You don't have to wait for me. So at 1 second, I'm sorry, 1.5 seconds, we're at 36 feet. At 1 second, we were at 16. So 36 minus 16 divided by 0.5. 36 minus 16. Again, don't wait for me. This is going to be 40 feet. And again, these are averages. So the average speed that it's going is 40 feet per second during that half-second interval. So go ahead and calculate the rest of them, and then pause the video, calculate the rest of them, and then come on back. Okay, this is what your data should look like. And again, we're just calculating the average speed over those half-second time intervals. So let's go ahead and turn the page. It says, compare the average speed between each time interval. What do you notice? Well, I'm not sure if you noticed it, so I'm going to give you a little nudge in the right direction. If I take 8 and I add 16, I get 24. If I take 24 and I add 16, I get 40. If I take 40 and add 16, I get 56. So it's going up. The average speed is going up by a time interval of 16 every half second. Well, that kind of makes sense because we said it was going to be 32 per second. or 32 feet per second, and 16 per half second kind of makes sense here. So over each time interval, there's an increase of 15 or 16 feet per second. So the time interval in 1 second is 16 feet, 2 seconds, 64, 3 seconds, 144, 4 seconds, 256. This is the same table, but it's flat. So a lot of our function tables are going to be flat now. Now they're saying time is t. That's fine. We can have time be t, but that's what we were calling x. So I'm going to conclude the video here. And what did we learn, or what were you supposed to learn in this lesson? That functions are used to make predictions about real life situations. For example, a function would allow you to predict the distance an object has traveled for any time interval. Constant rate cannot always be assumed. If it's not clearly stated, we have to look at various intervals and inspect the average speed. When the average speed is not the same over all time intervals, when the average speed is the same over all time intervals, you have a constant rate. When the average speed is different, you do not have a constant rate. We will, in future lessons, be figuring out what the equation is that actually will represent this information and being able to use the equation to make other predictions. So that is it for tonight. I'm sorry I went over, but this is actually something I'm teaching live. So if you were in class today, you actually didn't even need to watch this video. Have a good night. Talk to you tomorrow.